Hi students, in this class we are going to study a numerical problem on the nominal T method of medium length transmission lines. We have a three-phase transmission line. Its length is 100 kilometers. Resistance per phase per kilometer is 0.1 ohm. The reactance per phase per kilometer is 0.2 ohm. Capacitive susceptance is given. The susceptance is same as admittance. It is the inverse of reactance. Load power is given as 10,000 kilowatt. The load voltage is 66 kilovolt. Power factor is 0.8, power factor lagging. We need to find out the sending end parameters like current, voltage and power factor at the sending end. This is the nominal T network. The load power is given as 10,000 kilowatt. And the voltage is given as 66 kilovolt. The voltage given in the three-phase problem will always be the line voltage. So 66 kV is the line voltage at the receiving end. Here the power factor is 0.8 lagging. In this problem, we start with the receiving end voltage. We will find out V1 first, then we will find out Vs. We are going backwards to find the sending end parameters. Here the resistance is given as 0.1 ohm per phase per kilometer. We have a total length of 100 kilometers. So total resistance is 10 ohm. So 5 ohm is on the left side, 5 ohm on the right side, because they are R by 2 each. The reactance is equal to 0.2 ohm per phase per kilometer. Total length is 100 kilometers. So total reactance is 20 ohm. So on the left side we have J10 ohm. On the right side we have J10 ohm. Then the susceptance is given as 0.04 into 10 raised to minus 4 Siemens. Total length is 100 kilometers. So it is 4 into 10 raised to minus 4 Siemens. So capacitive susceptance is 4 into 10 raised to minus 4 Siemens. These are the network parameters, the parameters of the transmission line. Our receiving end voltage is VR is equal to 66 kilovolt. Actually, this is the line voltage. From this, we have to find out the phase voltage. We assume that it is a star connected system. So in the star connected system, as you know, the line voltage is √3 times phase voltage. So the phase voltage is equal to 66,000 divided by √3. So this is equal to 38,105 volt. This is the phase voltage at the receiving end. Is the magnitude, and in the vector form, as this is the reference vector, we can write this as 38,105 plus J0. We have to write all parameters in the vector form, in the A plus JB form, or in the R theta form. It should be represented in the complex form. So VR equals, it is 38,105 plus J0. As it is the reference vector, there is no imaginary part here. Now we will find out the current at the receiving end. As you know, P is equal to root 3 VL IL cos phi. These are the line parameters, line voltage and line current. If you use the phase quantities, then the power equation becomes 3 times V phase I phase cos phi. We use the line parameter formula. So it is root 3 VL IL cos phi. So from this, IL is equal to P divided by root 3 into VL into cos phi R. So this is equal to, here the load power is 10,000 kilowatt divided by root 3 into the line voltage is 66 kilovolt into the power factor is 0.8. So the line current equals 109 amperes. Now this is the line current, and in the case of star connector system, as you know, the line current is same as the phase current. So the phase current is also 109 amperes. So the receiving end phase current is 109 amperes. Actually, this is the magnitude of the current. We have to write it in the vector form. In the vector form, IR is equal to this current IR into cos phi R plus J into sin phi R. This is how we have to write it in the vector form. So IR is equal to, here the phase angle is phi R is equal to, cos phi is given 0.8. From this you can find out the angle. It is 36.86. As it is lagging, angle is minus 36.86. That is magnitude of the current 109 into cos minus 36.86 plus J into sin minus 36.86. And this is equal to 87 point, you get this is 109 into 0.8, because cos of minus theta is cos theta and sin of minus theta is minus sin theta, becomes minus J 0.6, and this is equal to 87.2 minus J 65.4 amperes. This is the receiving end current, that is equal to 87.2 minus J 65.4 amperes. This is the receiving end current. Now we are going to find out the voltage V1. So now V1 is equal to, because we are going backwards, V1 is equal to VR plus IR into Z by 2. This is our voltage V1, which is equal to VR plus the drop here. This is equal to, what is our VR? It is 38,105 plus J0 plus, what is our IR? It is 87.2 minus J 65.4 into Z by 2. It is 5 plus J10. So V1 is equal to 39,195 plus J 545 volt. This is our V1. So V1 equals 39, V1 equals 39,195 plus J 545. So this is our V1. Now we will find out this IC, the current flowing through the capacitor. IC is equal to the voltage divided by IC is the current flowing through this capacitor, that is equal to voltage by reactance. Reactance of the capacitor is minus JXC. It is equal to 1 by minus J equals J. V1 into 1 by XC can be written as the capacitive admittance. The inverse of capacitive reactance is capacitive admittance. So this is equal to J into, or V1 equals 39,195 plus J 545 into capacitive admittance is 4 into 10 raised to minus 4. So this is equal to minus 0.218 plus J 15.6. So IC is equal to minus 0.218 plus J 15.6 amperes is the current flowing through the capacitor. Now we can find out IS, where IS is equal to IC plus IR. IS is equal to IR plus IC. Our IR is equal to 87.2 minus J 65.4 plus the current through the capacitor IC is minus 0.218 plus J 15.6. So this is equal to 87 minus J 49.8. In the polar form, this can be written as 100 angle minus minus 29.78 degrees. So IS equals, it is 87 minus J 49.8. This is the sending end current. So in the polar form, this is 100 angle minus 29.78 degrees. Is equal to 100 angle minus 29.78. Now we will find out the sending end voltage. Vs is equal to V1 plus this voltage plus the drop across the transmission line, that will give Vs. So V1 plus the drop in the transmission line is current into impedance, Is into Z by 2. So this is equal to, or V1 is 39,195 plus J 545 into IS is 87 minus J 49.8 into Z by 2 is 5 plus J10 is the impedance on the left hand side of the transmission line. So this is equal to 40128 plus J 1166. In the R theta form, this is 40145 angle 1.66 degrees. So Vs equals, it is 40,128 plus J 1166. This is the sending end voltage. In the R theta form, this is 40145 angle 1.66. We write this IS and IR both in the rectangular and polar form, because we need to find out the phi s. Phi s is the phase angle between voltage and the current at the sending it. That's why we wrote these two values both in the A plus JB and in the R theta form. Where phi s is equal to is the angle between sending end voltage and the sending end current. So this is equal to 1.66 minus the angle of IS is minus 29.78. So this is equal to 31.44 degrees. From this we can find out the power factor at the sending end. Cos phi s is equal to this 0.85 lagging. Cos phi s is equal to the sending end power factor is 0.85 lagging. What is the receiving end power factor? It is same as the load power factor, it is 0.8 lagging. Now we will find out the transmission efficiency. Transmission efficiency equals the output power divided by the input power. Output is the receiving end power divided by the sending end power. So we have to find out the sending end power. Ps is equal to 3 Vs Is cos phi s. Either we can use 3 times the phase power, or you can use root 3 into VL IL into cos phi. These are the line values. But now we have the phase quantities with us. So it is 3 times the phase power. 3 into, what is our Vs? The sending end power here, sorry, sending end voltage. Here you should write the magnitude only. 3 into 40145 into, what is our Is? It is 100 into cos phi s is 0.85. So this is equal to 10275 kilowatt. This is the sending end power. So the transmission efficiency becomes, the receiving end power is same as the load power. It is 10,000 kilowatt divided by the sending end power is 10,275 kilowatt. The transmission efficiency is 97.32%.